the thing, the problem with Class A is it takes big hardware and it burns energy. Something that DIYers can afford to do. Manufacturers doing mass volume, they're in the same way that they don't have the opportunity to adjust for an amplifier for hours, they can't really afford to send something out that runs hot as a toaster. Okay, let's move on. Another characteristic besides the square law and the thermal stuff is, the capacitance. Bob's book deals with this very nicely, but I'm going to cover it in my own inimitable fashion. The MOSFET, you got these 3 pins. It's a 3-pin device. You've got a gate, a source, a drain. There are capacitances that are apparently in between. It's almost as if somebody took a perfect part and welded some little capacitors in those spots. Okay, there's capacitance between the drain and the source. There's a capacitor between the gate and the source and the gate and the drain. And they're all there. And they're all measured typically in picofarads. If you look here, you see all sorts of, I've got some where I got some parts where they're nanofarads, but none that where they're microfarads. And you know, capacitance in a part in and of itself, it might limit the bandwidth, but this is audio. We're not really worried about going to a megacycle. This is something where if you can make it to 100 kilohertz or so, you're doing okay. However, there's a bug in the ointment, which is, that the capacitance varies with what the transistor is experiencing. Most specifically, it varies with the drain to source voltage. In other words, the transistor, its swinging voltage is going plus and then it's going minus. It is referenced against a power supply that is a value above ground that is supposed to stay relatively constant. So what you see is that when the transistor is swinging voltage, the voltage across the transistor varies. Well, it makes perfect sense. Unfortunately, the capacitance varies as well. Now, when the capacitance varies, you experience a change in the gain of the part at high frequencies, because the capacitor has become part of that circuit and its value has changed with frequency and the gain of that system has been altered. It may be what we think of as a linear alteration in the sense that it's gone from one value to another, but it results in nonlinear performance because distortion almost invariably could be looked upon as variations in gain of the active parts. When a transistor goes, setting capacitance aside, when you put different voltages across a transistor, drain to source, or when you run different amounts of current through the transistor, the gain will vary. And when the gain varies, that creates distortion. It creates those harmonics and stuff that we've been looking at previously. Well, when the capacitance varies with the voltage, at high frequencies, the gain is being changed substantially, and you have a whole new set of distortions that creep in. And so you have a problem with all kinds of devices, but in particular, it's a real problem with MOSFETs. And I'm going to show you how that shows up, and also pinpoint one of the worst. People look at these figures here and go, wow, what's that? CISS, that's the one that's really going to be the problem. Actually, probably not. It's the one at the bottom, CRSS, which is the capacitance from gate to drain that's really going to kick your butt. Next slide, please. Now, just apropos of this, though, here's an example of capacitance on these stages that we've been looking at, right? So I'm running a frequency response, and you can see the gain of the thing in decibels. And at the top, what you see is that circuit being driven by a low impedance source. In this case, the audio precision will give you 25 ohms. That's why I'm using it. So it's got a 25 ohm source impedance, and you see that it makes it out. It's less than a decibel off at 200 kilohertz. That's pretty flat. And by the way, I mean, as a rule, these things are pretty flat. They're followers. If, however, you change the source impedance on the oscillator to 600 ohms, all of a sudden, it drops off a lot faster and you've lost bandwidth, okay? This is the first effect that you see, which is the capacitance of the devices affect the actual, just the bandwidth, the frequency response of the part. And they don't raise it. Can I have the next slide? The distortion. Okay, these are the same old FETs. By the way, we haven't degenerated these FETs or anything. They're still running without the resistors, so that you have a reference. Not that it particularly matters in this case. This is distortion versus frequency for that same kind of a circuit. We're running them at, we're running them at a couple of watts. It's no big deal. But what you see is that the distortion is different with 600 ohm, which is the top one, and the 25 ohm, which is the bottom one. You can see that while there's some differences down here, which are probably my measurement apparatus really, you've got a widening gap in distortion. The distortion goes up at high frequencies to the capacitances in the transistors. Next slide, please. I hope I'm not running too late. Oh, let's skip the questions because I think I am running late. Next one. Oh, but I did want to talk about a part that was like almost none of these problems, and these are laterals. Laterals don't have a lot of gain. They don't have a lot of transconductance. Typically, half to a third or even less the transconductance that we get with like those international rectifier parts. If you set the bias at a particular current, this would be a fine example, they don't wander around with the bias. And they also have really low capacitance, okay? And let's see what else is really good about them. If you buy the right ones, and these are the all-FET parts, they really have a quite good match. And we're going to see some of the performance on those. One is that, in this case, this is, by the way, this is distortion on those laterals against bias. So we go from 0 to 20 watts. At the top, we're running half amp bias. At the middle, we're running 1 amp bias. And at the bottom, we're running an amp and a half. And you can see the distortion just keeps going down. And you can see that it's not going to go down forever, and you can kind of sense that maybe your payback on bias is not going to be as great as you keep increasing it. But this is one of the reasons why you like Class A, is you can actually see this stuff there. Next. This is that same lateral, and we're looking at the curve through the N-channel part, just like we did with the IR parts. This is under the same conditions, okay? In this case, it actually just goes down and touches at 0, okay, under those circumstances. But look at this. It's still clean, and it's not flat. The IR parts at that point would be flattening out more, and you'd see it. So that even though the Class A region isn't quite as extended, it's really nice and clean. The laterals are really good at this sort of thing. Next one. And here's the lateral capacitances. The CRSS, which is the one we really I'll show you elsewhere where we have problems with that. It hardly varies at all. And look how tiny it is. I mean, the other scale is getting up into the thousands. So this is sitting out here in the CRSS, which is the drain to gate capacitance. They're not even giving us a value there. I mean, I don't know, maybe that's 10. Typically, that's a good figure for that. Also, it hardly varies with voltage. The COSS, I don't worry about quite as much because it's on the output end. It's somebody else's problem usually. And the CISS, which is the gate to source capacitance, is kind of high, but it doesn't come apart till you get down to about 2 volts across the device or so. And it's not that high. It's low by comparison to showing the vertical parts from IR and so on. The other thing you have to remember is that the gate to drain sees the full swing of the amplifier. The gate to source only sees the little small voltage swing between the gate and the source. And so it can have vastly more capacitance and still not have anywhere near the effect as the much lower value of capacitance that you see on the gate to drain. Next slide, please. Questions? Oh, you probably want to know, well, why aren't we just using laterals? Well, okay, a couple of reasons. One is the gain is really low on them, okay? And so, for instance, I built a very nice amplifier called the F7, which has complementary lateral parts and is a 20-watt amplifier, has only 4 transistors in the whole thing. It's a really nice amplifier. Everybody said so. Oh, you know, it sounds good, but it just got, you know, something. It's not. Well, what it didn't have is that it didn't have quite enough poop to control the load. It didn't have, actually from a measurement standpoint, it didn't have quite the damping factor. It had a damping factor that was, I actually forget, but it was like 10 or something. It wasn't real high. But the distortion was real low, the bandwidth was halfway to the moon, it was quiet, it had everything on your measurement checklist, but you know, my listener Joe went, I need some help. I'm going, why? You know, I can put a resistor in series with the load to simulate this. How come you don't hear it then? He doesn't know, but he can hear it. Well, I could hear it too, but I wanted him to tell me. Anyways, the thing is, it just didn't have it. I had to employ a trick using what's known as positive current feedback to get the damping factor back up, and now it's out there getting great reviews with the lateral parts. But then it required a trick which I haven't seen used since the 50s for tubes. The laterals, somehow they just seem to lack the dynamics. I don't know how to explain it, because you could imagine that you could parallel enough of them up, or you could find some other way around it. I think that you can. But usually everybody at that point is just going, what a pain in the butt. There are people who like the laterals anyways and love them to death. I run across them. They form their own cult, as it were.
They just don't need thermal compensation.
There you go. And these guys don't need that much in the way of dynamics or damping factor. They have polite loudspeakers and they listen to polite music. Next one, please. So, but here's the opposite case, okay? Here's a mega transistor. Ixis is this company that makes big die vertical MOSFETs in packages that I like to call hockey pucks. There actually is a bigger package literally called the hockey puck, but these are big. They're called, the package is an SOT227. It's rated at 800 watts. Okay, these other guys, by the way, they're doing real good when they do 100 watts, maybe 150. These are 800. And the transconductance on them, the lateral transconductance figures are like a 1. You put 1 volt difference on the gate and you get 1 amp for your treble. You put 1 volt difference on these, you got 60 amps. You got smoke flying all over. They have huge gain, and as followers, they are just like, they're a lot of fun is what they are. And if you like to play with muscular parts, then you're into it. So these are Ixis parts. There's an N and a P. I'm not giving you numbers because they have a bunch of them and they all kind of do this. So I'm not even bothering to identify which ones, because I've made a collection. I still haven't even decided which one I'm going to use myself. You bias them up. This happens to be typical kind of bias figures. There's a little difference in that, but these numbers are real numbers that gave me the right bias and put 0 voltage offset at the output. Next. And they're operated without transconductance, you'll see. They have huge capacitances. Remember that 10 picofarad down there that we looked at with the laterals? Okay, well that same part, it's up in nanofarads. Look at this. We've got 10 nanofarad CIS has more, you know. Excuse me. This is one of the reasons, by the way, that we always try to leave some voltage left over for the FETs. And when I design an amplifier, and I really actually want it to perform well so that John Atkinson will, give it some good-looking curves in the magazine reviews, and in general, I leave some voltage left over between the supply and what I expect the amplifier to be run up to when it's at rating. Why? Because as the voltage goes down, all this stuff goes to hell, and your distortion curves, start leaving the graph that they like, and so on and so forth. This occasionally results in reviews where the guy goes, it's a 25 watt, oh my God, it does 100 watts. Well, that's the extra voltage that I left over, so it would be super clean at 25 or 30 or whatever. So here's a trick for you. If you're designing an amplifier and it's MOSFET, even if it's a lateral, leave some voltage left over. You don't want to operate in that zone where there's only a few volts across the transistor. Give yourself a little margin on that. In this case, you might want to consider a lot of margin. But I have an example of one of these back on our display, which I'm sure it'll still be there when I get there. And I leave 10 volts. And 10 volts keeps me down in these regions instead of up there in the corner. Next slide. These are the excess parts with, you remember that test that I talked about earlier? 1 watt, 25 ohm versus 600 ohm source impedances. Now, here's why I'm showing you this is that, first off, those are pretty good curves. In fact, up at the top, it's even a little better than we were getting with the IR parts. But you see clearly that the capacitances do start coming into play, and in this case, you're 3 dB down somewhere above 100K. That's not very tragic. I deliberately limit the bandwidth of my amplifiers to around 100K, because in the old days, I used to get amps blown up because they had really flaky wiring and they had no shielding on the interconnects between the amp and preamp, or the guy didn't ground the case of his volume control on the design. And so you've got a demo going on where the guy's holding a switch box in one hand and his hand touches the volume control, and the whole system forms a huge oscillator, and then smoke comes out of everything, and then I get the call. But if I limit it to 100 kilohertz or so, that doesn't happen. So I can build 1 megacycle bandwidth. I choose not to. That's part of the sleep at night scenario. But the excess, what's interesting is for all that hugely greater capacitance, it isn't so bad as long as you keep some voltage across the FET. And next slide, please. Here we go, distortion versus frequency. And I wanted to show you this because I've got the 3 parts with 4, 8, and no load scenarios. The red is the no load, you might guess, because it's the lowest distortion and so on, and the 4 is at the top. There will, at low frequencies, be obviously some difference between no load and having 8 and having 4. It's not a huge difference, but the distortion will ramp up as the transistor has to do some work. What's interesting is that the capacitance, we're swinging the same voltage for all of these. The capacitance, which is the CISS, is the one that's actually being varied significantly. And what you see is if the distortion is due to the gate to source capacitance, you're going to see these guys diverge quite a bit because the fact that you're charging that capacitance. And what we see is they don't diverge. They all go up about the same amount. Next slide, please. And let's see. Oh, that was with a 25 ohm source. With a 600 ohm source, you see that they start earlier. Okay, the distortion, if you've got a high impedance source for these parts, the distortion starts earlier in the game and you get more of it. Notice too, though, that they still don't diverge between the loads. They kind of tend to follow that, especially up at the top end. They're kind of just notched up equally. Next slide. Okay, the reason I showed you that was so I could show you this. This is a cascade of the excess parts, in this case with other excess parts. And I built this one up. The cascade, and Bob's book will discuss this for you if you care to get a copy, sets it up so that the voltage across the gain FETs, okay, the ones that we've been looking at all along, is buffered out, is shielded by some additional transistors that are set up at higher voltages. They serve as if like voltage regulators, but they're floating. What do? Well, they let current through, that's no problem, but what they do is they hold the excess, the P and the N and the P channel here at relatively constant voltage, in this case something on the order of about 10 volts, but it's constant, okay? And the advantage, one of the advantages of cascading, and there's a couple, is that you're no longer charging the drain to gate capacitance because that voltage has been held as a constant, or at least relatively so. Next. And that shows up here. here's that circuit again. We have, well, first off, because the voltage is held constant, the regular gain at low frequencies of that transistor is held more constant. And you can see it in the distortion curve. Cascoding, the bottom one has got significantly less distortion than the one at the top. This is at a low frequency. I think this is at kilohertz typically. But we are looking at the fact that the cascoding in and of itself has lowered the distortion on these parts. If you want to spend the extra trouble, money, and so on to get the most out of your FET followers, or for that matter, your bipolar followers, or by the way, this works with tubes just fine. Cascoding is this wonderful thing because the cascode contributes practically no signature of its own to the performance. It's like having an umbrella in the rain. And the part that's doing the amplifying thinks that it's a sunny day, and all hell's breaking loose on the other side of the cascode. Well, it shows up in this performance, which is just at low frequencies, but the distortion is dropped by not quite a factor of 10, but I mean, this is substantial stuff. Next slide, please. Remember those ones where the distortion climbs with frequency because of the capacitance? Well, here we are with 600 ohm, the worst case. Here we are with the same kind of stuff. Oh, what happened? Where did the distortion? Oh, there it is. It's nothing compared to the non-cascoded parts at high frequencies. And this is one of the other beauties of this is all of a sudden your part is becoming far more perfect. The low frequency, the distortion associated with current has been reduced by a very large factor, and the distortion due to the capacitances from the gate to drain have been essentially nulled out, and you do see a little bump there. I mean, it would go up a tiny bit. I have a filter way up there that doesn't allow to show it, and the only reason I use that filter is that in this case I have noise on my bench, and you'd start seeing it. Cascoding kills that problem dead in its tracks. I did once upon a time actually market a fully cascode amp that had all the gain stages cascoded. People still tell me it's a really sweet sounding amplifier. But cascoding is kind of an obscure story as compared with, say, Class A or no feedback. And so I didn't quite see the market that it might have otherwise enjoyed because the performance was very good. So cascoding is also, the nice thing about cascoding is we were talking about trying to parallel parts up in an output stage to get bigger and bigger output stages. If you cascode, you can afford to have one part shoulder the output and use other transistors in the cascode and even degenerate them. And that one transistor, because it's on a low constant voltage, doesn't dissipate as much juice. You can get really high performance, much higher performance out of one device. Okay, we're into the home stretch. What's our time? What time is it?
You're 15 minutes over.
Oh, okay, I'm going to rush right through this. Sorry, Bob. Okay, I have, now I try to always bring something new, okay? This is it. I have an output stage which consists of a depletion mode part coupled with an enhancement mode part in a follower output stage. And here it is. The depletion mode part could be, depletion mode means that you have to actually apply negative voltage to an N-channel part in order to get it to shut off. If it's at 0 volts, unlike the other parts, it's conducting. So you got to have a negative voltage on it. It's kind of like any tube is like that. Meanwhile, the other ones are called enhancement mode parts because you got to apply the voltage. So it's like the difference between having an accelerator and a brake. This needs a brake. The one on the bottom, however, just like the P-channel parts we've dealt with so far, they need accelerators. What happens when you simply put the two together? Well, if you match the values of the depletion mode part against the enhancement mode part, it biases itself. Both gates are at the same voltage, and ta-da, you don't need a bias circuit. You have a perfectly fine Class A follower. It doesn't even have to be Class A, but that's the better way. And in this case, there are depletion mode parts available. I've got the silicon semi-south what are the name of those parts? Silicon something oxide.
Silicon carbide.
Silicon carbide, thank you. Silicon carbide parts, in this case the RO85s, but I got some other samples. And if you take a look, you'll find that IXIS makes a couple of depletion mode N-channel parts. There are no depletion mode P-channel MOSFETs that I've seen, and one authoritative text said they can't be made, and that's why. I don't know that because I've seen others made since that weren't supposed to have been made. So I said, well, this sounds cute, and I matched up the enhancement mode voltage of a P channel, in this case I had 9240, because I got lots of them, and a depletion mode part, and so that they had the same voltage, the complement, they run the opposite voltages for a 1.3 amp current. Hook the bases together, it self-biases, all by itself, no bias circuit. It does result in having a DC offset, so I got to capacitively couple the input, and I got to apply minus 4 volts or so bias to that whole system. But, you know, that's tough. That's really hard to do. This one shows a degenerating resistor between the two, and I played with that around a bit, and all that's for is if you can't get precise matches, you can put a little bit of resistance there and, you know, bring it in so you can tweak that in. Next. Here's the curve of that part. Here's the curve of that circuit, and with no resistance, because I actually had an exact match for that one. And you can see it's a 0.01. It's pretty decent looking. I've got snazzier looking stuff like this, but I happen to really like this circuit because it is so damn simple, and just the idea that it would just self-bias because of that, I consider to be a really cool thing. Next. Well, it looks like that. That's not such a bad waveform. I think that's about 0.01%, if I'm not mistaken, from the last curve. And it's a second harmonic. It's a negative phase second harmonic, which has a different sonic signature than a positive phase second harmonic. And my own preference is a slight amount of negative. However, at 0.01%, I'm not losing any sleep over it. Next. Here we are looking at the FFT of that part. You got your 0.01% or so second harmonic. Your third is about 20 dB down below that, and then you got your scattering of higher order harmonics, you know, somewhere in the parts per million section. Next. Oh, and here it is at 20 watts. Okay, that was a 1 watt curve. At 20 watts, you start seeing some other effects creeping in. That's such a pure distortion wave, so that it's still mostly second harmonic, but it's starting to come apart a little bit. And of course, at 20 watts, we're almost at clipping. So, you know, I've seen worse. Oh, and here they are. Here's the distortion curves against frequency for those two parts. This shows, just a moment. Oh, interestingly enough, the 600 ohm source resistance gave the lower distortion at that range of frequencies. That lower curve is from a higher source impedance, and it appears that there was a mismatch factor between the two devices such that it was being further canceled by the source impedance. So just as a fluke, it performs better with 6 ohms than a 25 ohm source. Next. Oh, and here's the old, you know, here we are hanging around on Class A again, and this is 20 watt 8 ohm. It's still holding Class A. It's not as dramatically good as some of the other parts that we have seen, but it's still exceeding expectations by some small margin. Next one. Now, there are those of you who will want to build this, because first off, actually it sounds really good. But the other end of it is, it might be a little difficult because you have to exactly match the depletion and enhancement mode values to get exactly what you want. Or you have to throw degeneration in there, and you may not even find a value that works for that. Now, I had these, in this case, I found that if I can get them matched within about 3 to 4 tenths of a volt, which is not so tough. I have a little trick circuit. That little extra couple of resistors that you see there will drag the enhancement mode part to a slightly lower current level. And by virtue of that, depending on how you want to set those values, and you can stick a pot there, you can exactly get that to balance out at any current level that you like. So you don't have to match them so precisely. Basically, if you can get them within 3/4 tenths of a volt, you can do this trick. And by the way, this resistor here is the one that created the lower distortion with the higher source impedance in the previous curve. So in point of fact, I'm looking forward to getting some of these built kind of in the same way that we did with the VFETs. In other words, we have a supply of these. You can also go out and get your own depletion parts and start playing with them. But from my standpoint, this is going to be the next interesting thing for DIYers to tackle. I have one of these all built and sitting in my display, but I left it in the box until after this talk. And when I go back, I'm going to take it out and fire it up, and if you want to come by and listen to it, you can. And, the end. Thank you very much.